In this lesson together, we will be discussing the PreLab questions assigned to us for our laboratory notebook for the lab called Determining the Molar Volume of a Gas. We're using a reaction between magnesium metal and hydrochloric acid, HCl. Through the process of what we know to be a single replacement, the magnesium can kick out the hydrogen gas. It is more active and therefore generate the hydrogen gas, and going into solution is the magnesium chloride salt. And we know based on charge, magnesium's a +2, chloride a -1, and so when we crisscross, we get aqueous magnesium chloride. The hydrogen gas that's generated will be collected and measured. To balance, I know that we'll need a 2 in front of the HCl, and this will also start aqueous, and the mass of the measured magnesium in its solid form will also be recorded. So the reaction for the day, magnesium metal, reacts with aqueous hydrochloric acid, generating hydrogen gas and leaving in solution magnesium chloride salt. If we begin with a 0.028 gram measurement of our solid magnesium, and we pour in lots of hydrochloric acid, so there is no limiting excess reagent here for magnesium, will be completely consumed. We measure 31 milliliters of hydrogen gas. So we capture and measure using our gas collecting tube. So this is what we call our experimental value. In our lab conditions, we collected 31 mil of our hydrogen gas. Whoops. There we go. So just to kind of bring us up to speed, we walk to the scale, we take a little piece of magnesium ribbon, we weigh it, and it's 28 grams. We place it in a reaction tube called a gas collecting tube, and just to remind ourselves, it's on our website as well. A gas collecting tube is like a long inverted graduated cylinder, and we place it in a beaker full of water where the little piece of magnesium is being held secured by a copper wire, and as the acid which is in this tube falls down and finds the piece of magnesium, the reaction proceeds, in which you literally start to see are the gas bubbles of hydrogen form. And so by the time we're done with the experiment, we just simply read on this graduated tube how many milliliters of hydrogen were collected. And we do so when the water levels are equal. We equalize the water levels inside and outside here to make sure that the barometric pressure matches the pressure in the tube. So our first question asks us to apply Dalton's law and the vapor pressure of water at 22 degrees to calculate the partial pressure of hydrogen in the gas collecting tube. Dalton's law just simply states that the total pressure inside of this gas collecting tube is actually coming from a blend or a mixture of two gases. We'll have the hydrogen gas that we collected, but because we collected it through water displacement, we have a little partial pressure of water to consider there as well. So the total pressure came from reading the barometer. The total pressure in this experiment was recorded as the barometric pressure of 746 millimeters of mercury. And using your table, which is on the previous page of your lab report, using table 1, we simply look up the partial pressure of water at 22 degrees Celsius, and when we do so, we can find the water contribution to the overall process. So this, we just simply used our chart at 22 degrees Celsius. The partial pressure of water is 19.8 mmHgs. And knowing that the total pressure is the sum of those two, we're going to simply subtract and find the contribution of just simply the dry hydrogen gas. So my total pressure, reading from the barometer, 746, minus the partial pressure of water, which was recorded as 19.8, leaves us the 726.2 mmHgs for the partial pressure of the dry gas. So we'll record that 726.2 millimeters of mercury is our partial pressure of the dry hydrogen. So anytime we collect a gas by water displacement, we understand that in addition to the hydrogen gas that we're collecting in this tube right here, we also understand that there would be some water pressure in there as well. And we just look up on our chart and subtract out the water's contribution from the barometric pressure. Let's use the combined gas law to calculate the corrected volume at standard conditions, STP. So here we have our pressure for the hydrogen gas given to us. I'm going to try to make this neat as I write. The partial pressure of hydrogen gas is recorded as 726.2 mmHgs. The temperature at which we recorded that was 22 degrees Celsius. And the volume that we recorded, and notice here, this is coming from the data provided, was 31 milliliters. Alrighty. Before I go much further, I'd like to know 22 plus 273, simply because we always have to know the Kelvin temperature for our any of our gas law calculations. So I added and found 295 Kelvin units. So these are what we refer to as our experimental conditions. And in the experimental conditions, we'd like to set it equal to STP and solve for the new volume. So standard pressure in a like unit we know to be 760 mmHgs. Standard temperature is 273 Kelvin. What would the volume be had we ran our experiment in those standard conditions? So we'll use our combined gas law. Having all 5 variables, we'll pull out the missing 6th one, the V2. So our first pressure, 762.2 mmHgs, times our original collected volume, 31 mils, over our temperature of 295 Kelvin units. Set that equal to, and since I'm out of room, I'll just come down here, but these two are going to be set equal to one another. 760 mmHgs. Looking for V2 when T2 is standard temperature 273. So we're setting standard conditions equal to our experimental conditions and adjusting the volume. Had we run the experiment when our lab was at standard temperature and standard pressure, this would have been what our gas collecting tube would give us. So let's solve for V2, and to hit that, keep in mind we're going to take P1, V1, T2, divide by the product of P2 times T1. And I'm just sharing with you how we're going to rearrange pulling out that corrected volume. So my calculator would begin by hitting 762.2, that's my pressure 1, times 31, that's my first volume, times 273, that's my second temperature, equals, large number, divided by parenthesis, the product of 760 times 295. Again, that's P2 and T1. Close my parenthesis, hit equal. My new corrected volume, when I solved for that, came out to be 28.77 mils. That gets placed in the data table in our lab. So our new corrected volume, 28.77 milliliters. We stood in a little warmer conditions and at a little lower pressure and measured 31 mils. Had we been at standard conditions, we would have measured 28.77 mils. Our third question asks us to find the theoretical number of moles of hydrogen that can be produced from 0.028 grams of magnesium. So here we have our magnesium reacting with our hydrochloric acid, generating hydrogen gas, and leaving in solution magnesium chloride. We're given the number of grams of magnesium and like to know the moles of hydrogen. This is just an old-fashioned stoichiometry roadmap. Given a mass, calculate a mole. We know in our first step, we'll take our grams of magnesium, and to convert it to a mole, we use its molar mass. We find on the periodic table the molar mass of magnesium. It is given to us as 24.3 grams. In the heart of our stoichiometry problem, we have 1 mole of hydrogen generated for every 1 mole of magnesium consumed. And I'll just hit for us our little mole map here. We have 0.028 divided by 24.3 times that 1/1 ratio, and I found a value of 0.00115. There's my molar value for the hydrogen. Given a mass, we calculated a volume of hydrogen. Let's convince ourselves that this is something we can compare to standard values. So let's go back up here and find that 28.77, our corrected molar volume in milliliters. 28.77 mils was our corrected volume. And we want to put that into a liter. So remember that a liter is actually 1,000 mils. And we're going to divide that by the number of moles we just solved for. Alrighty, so we're finding for molar volume in terms of liter per mole. Our corrected volume was 28.77. I'm going to divide that by 1,000 to make sure I have it in a liter unit. Alrighty. So you can see that would be 0.02877 liters. Divide that by 0.00115, the moles of hydrogen, and I'm finding a value of 25.017, around 25.02 liters per mole. Now in our lab, we'll be asked to calculate percent error for our experiment. It's the theoretical value subtracted from our experimental value. Subtract them in either order and make it always an absolute value and express that as a percent. We've learned that the molar volume of any gas at standard conditions is always 22.4 liters. I calculated mine to be 25.02 liters per mole. Remember to subtract that, but always make sure that you're looking at it as a positive number. And let's see how well this experiment worked. 22.4 minus my experimental value, 25.02, hit equal. Ignore the negative. Divided by my molar volume of 22.4, expressed as a percent. This particular lab had an 11.68% error. The closer you are to 22.4 by the time you're done calculating, a little bit more precise your experiment came out. This isn't terrible. It's just what this particular data set showed us. So the purpose of our lab coming up this week, you're going to measure out a mass of magnesium ribbon. You'll react it with a excess amount of hydrochloric acid in a gas collecting tube. When the magnesium ribbon is consumed, when it's all gone, you'll measure the amount of hydrogen gas you collected at equal water levels. That then is used through a series of calculations to turn it into an STP value and then compared to the molar volume of 22.4 to test for your accurate results. See you in lab this week.